Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I hope get you started with Class 18 on hypothesis testing, where we will use two sample data for our tests. So I'm going to scroll down to Class 18 for hypothesis testing, and this has its own assignment separate from your project file. So we will download the markdown file. Okay, it was already in that folder. And we've got two data files here. This first data file, as you can see from the address down here, is from class 13. So you already have that data, but you can download it again. It's okay. And then this one is new for class 18. It's a new data set, also class data that we collected from previous years. All right, let's start our studio, and we will open up the markdown file and knit it. This file also requires the, page down for a moment, the ADA functions.r file, which on the website, if you don't already have it, is, if you scroll up above the timetable, I actually have it, I think, yes, at the bottom of all the lecture notes and stuff. So here's the section on the course notes here, and so if you scroll below that table, it is basically like a supplement on that section. So make sure that you have the current version of that in your folder. I know that I have it, but what the heck, I will download it again, make sure it has the same file name, and overwrite it, and we'll use that today. All right, let's open this up in the browser and scroll through the assignment. So you've got three problems to do. We're going to look at testing the height data for our class, not our class this year, but in previous years, classmates measured their hand span in centimeters and their height in inches. And we're going to ask the question of whether our average height for females and males is equal or greater than the average height for the U.S. population. Okay, so I'm going to show you an example where I walk through the entire thing with females, and then you get to do it, your turn, you get to do it with the data for the males. Then we're going to do the same thing, but testing, so that's for the population mean. This is for the second example is for a population proportion for the, proportion of water on Earth. And then the third example is for, that's weird, I closed. And the third example is a two-sample problem where we're making a comparison, a difference between two means. All right, let's scroll down in this document. I'll walk you through my example, and then we'll discuss the other parts. Okay, so I would like to start first with the mechanics of a hypothesis test, or as some people say, an hypothesis test. It has 6 steps, and some of these steps require more work than others. The most important step in my view is the first step of setting up the hypothesis. There are 2 parts. There's a null hypothesis, which is typically what the statement of nature when things are boring and not interesting, okay, or not changing. So this is of equality, when things are equal. And then there's the alternative hypothesis, where things get interesting. Oh, there's a difference, or things changed. Okay, so in words, I will ask that you state the hypothesis in terms of the alternative hypothesis, because as you saw in the lecture notes, there's three forms of the alternative typically. There's not equal, which is a two-sided test, and then there's two versions of a one-sided test, that the true population mean is greater than a specified value, or it could be less than that specified value. So whereas the null hypothesis is always equal to in the way that we're doing it in our class. So it's not interesting to state things in terms of the null, because the alternative is where all the action happens and where the choices are made. So in words, we'll say the population mean for whatever it is that you are studying, for so the population mean for, statistics students, male statistics students or female statistics students is different from, or greater than, or less than, a specified value, 60-something inches, based on the average of the U.S. population. Okay, so you basically follow this example, and that is your hypothesis. And I want you to always state them in words and notation, so that you have practice saying what the hypothesis means, so that anyone can understand it, and then engaging with the notation a little bit, so that you are using some of these symbols, like mu for mean. Mu naught is a specified value from your hypothesis. It's something that you choose. Okay, so that's step one. Step two, you choose a significance level of the test. It's almost robotic for everyone to just choose alpha equals 0.05, because Ronald Fisher did that in the late 1920s. And this basically says that your type 1 error is 5%. So the likelihood that if the null hypothesis was true and you incorrectly say that it is false, right? So assume the null hypothesis is true. If it actually is true, you have a 5% chance of rejecting the null and making an incorrect decision. Other popular values are 0.1 or 0.01. And I believe it should be chosen based on the context of the problem, but unfortunately in most of science it is just chosen to be always 0.05 without thinking about it at all. Number three, compute the test statistic. So this is where you start, where you put the data into an R function and compute the statistic. And so for a mean, you'll have a statistic t, which can be calculated, as I discussed in the notes, with a certain standard error. Step 4 is to, based on the alternative hypothesis up here, determine the tails of the sampling distribution for which we will calculate the p-value. Okay, and the p-value is the probability, the probability is, the p-value is how consistent the data are with the null hypothesis. Okay, so if the p-value is large, then that supports the null hypothesis. And as the p-value gets smaller and smaller, you're starting to get less and less support for the null hypothesis, and effectively more support for the alternative hypothesis. And ultimately, if the p-value, as in step 5, if the p-value is less than the alpha level that you chose in step 2, then you're going to reject the null hypothesis in favor of the alternative. Otherwise, if the p-value is large, then you're going to just say that the data are consistent with the null, and you fail to reject it. Now, we never accept the null because we are assuming the null hypothesis is true. And so we're not claiming, we're not doing anything more than just, we assume that it was true and the data were consistent with that. We're not proving that the null is true. Okay? We just say that we couldn't reject our assumption. The data are consistent with it. Okay, and finally, we would check the assumptions of the test, And there's some arguments to be made that you perhaps should check the assumptions earlier. The reason I'm putting it way down here is because we're not going to do this week. We're going to focus on these first 5 steps of the hypothesis test, and we will start checking assumptions next week. In practice, you might consider stating the null hypothesis. That will and the alternative hypothesis, that will give you a sense of what the sampling distribution is and what parameter you're testing, such as mu. And then you can go ahead and check the assumption maybe as step 1b, and see whether it's worth going through the rest of these steps or not. Or perhaps you need to take a transformation, which changes the parameter that you're testing. So before you do all this other work, check the assumptions earlier. Okay, that was a lot of talking. Let's get on to our examples. So we collected height data from our classes, and we want to know whether students in our class, historically, are different than the average heights of men, which is 5'9½", or women, 5'4", in the U.S. So we load the tidyverse packages in, we source our functions because we're going to use that later on, and we read this CSV file and make the gender variable a factor variable. And when we look at the structure of that data set, we've got which semester we're in, whether they're male or female, their height, and their hand span. So we're going to be using the gender and height in this example because we're going to use all the semesters of data. Okay, so first thing I do is I'm going to create a plot, and let's go look at the plot, and then I'll come back up and we'll look at the code that I'm doing up there. And I've got a lot of stuff here. All right, here's 2 versions of plots of this data. On the left, we have gender on the horizontal axis, female on the left, males on the right. We have their height in inches going up. And we've got blue diamonds for the U.S. population. That's the what I labeled as true. That's the true value of the U.S., the average height of the U.S. population. And the red circles are the estimates from our data, or from our class data. Okay? And all the black dots here are heights from people in our class. And we've got a box plot here so you can see where the median is and the middle 50% of the data. The red dots seem to be higher than the blue triangles. So it looks like heights of students in our class, both for females on the left and males on the right, we're taller than the U.S. on average. Another way to look at that is with the histograms. I think I prefer this view, but I think they're both quite good. The females are the facet on the top and males are the facet on the bottom. We've got the histogram of the heights in inches on the x-axis, and we've got the blue line is the true U.S. population, and the red line is the average from the estimate of our UNM students in our class. So we got maybe I don't know, what difference is that? Maybe an inch or so, maybe also about an inch here, maybe an inch and a half. So it shows the same information. All right, I want to spend a moment looking at the plotting code, because we've not just plotted the data in the gray histogram, but we've overlaid these other values, and I want to show you how I did that. I also created this plot layout where the box plots take up a little space on the left and the histograms take up more space on the right. And I want to show you how I did that as well. So it's likely that I will break this video into 2 pieces. Okay, let's see. So I've read the data set in here, dat_hand. Okay. And we want to plot the estimated mean from our class versus the true U.S. mean. So the first thing I do is, let's see where I've got okay, I want to make this table. This table here has the gender, female, male, female, male. I've got the heights, and I've got what data source it came from. These top two rows are the estimates from our class. You can ignore the dot groups. I don't know why they keep showing up. So our estimates for females is 65.2 and for males is 70.3. The true values from the U.S. population for females was 64 and 69.5. Okay, so I'm creating this little table. I'm going to come back to how I do that in a second. And what I end up doing with it is I start by, let's look at the histogram code. I don't know, they're exactly the same. Okay, let's look at the box plot code, right? So the box plot code produces this plot on the left. So once I create the box plots and the black dots, the geom points, then I'm going to add these blue and red symbols. So look at the box plot code. So I put in the dat hand. Oh, let me do one more thing. This table is in this object, true est. That's because there's like the true US values and the estimated from our class, and these are the means. So true est means is our table data set. So I start by plotting the dat hand, and I assign gender as the x variable, y as the height. I put the box plot on there, and I jitter some points. Okay, that there would create the data, the standard plots. Then I augment it, and in the geom point, I've got a new data statement, just like I had up here, but now I'm putting in just this table of these means, and I've got the same variables in there, right? I've got the gender and the height, just as I had for the gender and the height in the original data set. Because I've labeled them the same, it knows, for geom point, it knows that the gender from the true estimate mean, the gender goes on the x-axis, the height goes on the y-axis, and then the only other things I need to assign is some way to distinguish these points. And so I'm using the true estimate column to define the color, so that these two groups will have different colors and they'll have different shapes. The last thing I did is I made them a little larger. Size 4 is pretty big, and alpha is less than 1, so they're a little bit transparent. And finally I put a little title on there called box plots. So if we scroll down and take a look, now I've got the color and the shape is different. ggplot automatically made this legend for me, and it put the dots on there, and they're a little bit transparent. You can see some black dots through the color. Okay, so that is a fairly nice way to overlay some summaries on a plot. And if you look at the histogram code, it's basically the same. The only difference here is that after I've plotted the histogram, right? Okay, let's start at the beginning. Here's the det hand. I assign the height to the x variable. I'm going to create a histogram, and I specify the bin width of 1 inch. Then my annotations, my augmentations, are these vertical lines, where the x-intercept of the vertical line is the height in inches from that true estimate table. And I also specify a color, but not a shape this time, but a line type. So we should have, we have a solid line for the estimate, and we have a dashed line for the true. Okay, and the last part is I did a facet grid so that and by row, so the gender is in the row, tilde, the column is a period. That means we're not going to facet it by columns. So we've got rows for gender, and that creates the row for females and the row for males. Okay, the last part for plotting, and then I'm going to go up and describe how I created the table. So I use this quite a bit when I'm submitting papers for publication, for laying out a bunch of plots together. In the library's grid and grid extra, I believe the grid extra gives us the layout matrix, but I don't remember at this point. I'm going to arrange in a grid my plots. And I've shown you examples of this before where we just had the graphical objects and you list plot 1 and plot 2, right? In this case I've got plot 1 is the box plot and plot 2 is the histogram. So you list those out, and sometimes instead here I would say that the number of rows equals 1, and you can specify it in that way. Well, I knew that after trying it that way, the box plots were way too wide and the histograms were way too narrow. They were squished. And so I decided to create this layout. And so you can create a layout like this where plot 1 is going to take 1 unit of width and plot 2 takes 2 units of width. And that you can actually add multiple rows here so that you can also specify their heights. And you put that into an object. I call it lay for layout. And in my layout matrix, I specify that. And the grid arrange does everything else. So the grid arrange took those plots and it made the box plot 1/3 of the width, and then took the histograms and made it 2/3 of the width. That, I think, is a very nice way of laying out plots when you have multiple plots. Okay, last part of all this. I know this is all just talking about code. All right, here's the last part. So there's two parts that go into this table. There's the estimates from our data, and then there's the true values from the US population. So I need to create those two parts. So first I'm going to create from our data. Here's the estimated mean. I start with the data set, I group it by gender, and then I calculate the mean height. I summarize and create the mean height for each of the groups. This argument should not produce. It's there so we don't get a warning, but then sometimes it creates a weird column in the data set. Anyway, I'm getting this is a new option that they added to summarize in the last couple months, and it seems to not be working quite right always. Anyway, so I grouped it by gender, I calculated the mean, and then I ungrouped the data set, and finally I specify here a new column, true estimate, where this is going to be labeled as estimate. Okay, so in this table, these are our estimates. That is effectively the first 2 rows of this table here. Okay. Next, I create a row-wise tibble, called a tribble, where I specify the gender, the height, and that these are the true U.S. heights from the U.S. population. And from the Wikipedia page, I've got females and males, and I've got their heights in here. Okay. Finally, I need to put these two tables together, and that's what bind rows does. Because they have the same column names, they both have gender, height in inches, and true estimate. I can start with our estimates and bind row-wise the true means from this table, and now I've got my true estimate mean table, and it took the true values and bound those row-wise to the estimate table. And when in the true table it didn't find the dot groups variable, it just filled it in with NAs for not available. Okay, that was a lot. Anyway, we've produced a beautiful plot. So I think what I'll do is I will, so we've gone through the code that creates that creates this plot. Let me see what else I can do. I think I want to break this into 2 videos, and I want to sort of put all those things together. Maybe it's worth. Let me cover all the plots in this video, and then I'll come back and do a second video where we do the hypothesis testing. All right. In the Earth's water example, we have we saw 21 successes out of 35 tosses of the beach ball, of the Earth beach ball. 21 times we saw water, and the 14 times we saw land. And this is the same data that we saw before. We created this little table where I calculated proportions. Next, I'm also going to create a plot. And I believe that I've got a mean in here somewhere. Oh, I see. I put it in this way. Okay. So in the plot, I've got my data set. We're just going to plot the water. This is the same plot as we did before, and I believe we even did this part before, where we put in the confidence interval. This time we're going to do the hypothesis test, so the confidence interval is not that interesting to us, but it's sort of useful for visualization. The part that we are doing new is we've added this line, where we've added a horizontal line. Remember, before we flipped the XY coordinates, this red dash line was horizontal and not vertical. And we specified the y-intercept as 0.71. That is the true proportion of water on the Earth's surface. And I've specified the color to be red, and line type equals 2 is a dashed line. And so that is the annotation on this plot. The last annotation is the caption, because it's helpful to know what these black bars and red lines are. So I've said red line is 71%, which I probably should also say, the actual proportion of Earth's surface covered by water. And the black bar is a 95% confidence interval. And those appear down here at the bottom, in the bottom right corner of the plot. Okay, so let's scroll through the last example. So we conducted an experiment based on, what's that guy's name? He's a Nobel Prize winner in behavioral economics, Thinking Fast and Slow, Daniel Kahneman. In Daniel Kahneman's book, now a lot of Daniel Kahneman's experiments don't actually replicate, but this is one that does replicate, and it has to do with a priming effect, that if you tell someone something, you can change their response to a question that should not be affected. And in fact, this is what we did in a randomized experiment. And in each year that we did this, in 3 years, we had a very, very strong effect. And I'm going to choose the fall 2019's data because it was the weakest effect. And so the other years were much stronger. Anyway, here we go. So we had a randomized experiment. We provided a priming number, either a 10 or 65. Just at the top of the page, it said, your random number is 10, or your random number is 65. And it had no bearing on anything. It was just a number, okay? And then we asked 2 questions. First, do you think the percentage of countries represented in the United Nations that are from Africa is higher or lower than your random number? Okay? So this question is just intended to make the person engage with this priming number. Okay, so if you think that the proportion of, right, so there's almost 200 countries in the world, how many of those are from Africa? Even I don't really know right now. In a way, it's not that important to the actual experiment, but, there are a lot of countries in Africa. So maybe 20% of the countries in the UN are from Africa. That might be my guess, sort of naively, okay? So I would say if I got the 10, I would say it would be my 20% is higher. If I got the 65, I would say that my 20% is lower. Okay, so I would indicate that. And then give your best estimate of the percentage of countries represented in the United Nations that are from Africa. Okay, so 20%. And that would be the values that I put. When you read this data set in, I've got my priming number, whether it's a 10 or 65, and I've got whether I said it was higher or lower. And in this case, I'm also filtering it for just fall 19. Let's look at the structure because there's also the UN percentage, which is the numbers that people said, right? So the first person said 3% of the UN countries are from Africa. This person said 25, etc. Okay. And it was the case where some people were inconsistent, but not very many. Where like, actually, is this a person? This is a person. This first, oh no, hold on. No, it's hard to tell. But some people, for example, would say like 3%, but say it was higher than 10, something like that. But that didn't happen very often. Okay, so now I'm going to create some summaries. I group by the priming number, either the 10 or 65. I calculate the mean UN percentage, and then I'm going to create a plot that plots histograms and puts those vertical lines based on the means that we calculated in this code where we grouped, and let the x-intercept be that UN percentage, and I made red lines. And I faceted by the priming number, which gives me the 10s up top and the 65s below. Now, this is the awesome strength of priming. Now, we just gave them a random number, a 10 or a 65, and that influenced whether someone guessed a number that was low on average or a number that was higher on average, right? The 10 and the 65 was told to the students that these are random numbers, had nothing to do with anything, but just making the person think about, what do I think about UN proportion relative to this random number, that affected their guesses. The small numbers drove them down, and high numbers drove them up. So, think about in this life, think about situations in your life where you can use this psychological trick to your advantage, but don't use it for evil. All right, I do have another type of plot here if you want to uncomment it and take a look. This other plot, instead of having facets where we've got 10 and 65, this plot right here overlays the two plots. So position identity means that the two histograms, these two histograms lay on top of each other. And I make the alpha level 1/2 so that they're transparent, and you can see the two distributions lay on top of each other. I think that looks cluttered, and I really like the clean look of the facets. Okay, and then there's a t-test question to answer. So I think this is a good place for me to stop, break the video, and we'll come back in the second video and actually do the statistical portion of this assignment.